introduction there. So my talk actually follows on very nicely from the other talks we've had today. So thank you for setting me up. And this wasn't planned. So today I'm going to talk about some controlling of plasmas rather than sort of the background to modeling or the sort of business side of things. It's what do you do if you've got a plasma in a box and you want it to do a certain thing? Here are some of the ways that we can do that. Does this work? The recurring feature. There we go. This seems to work. So, agenda then. I'm going to go through plasma uniformity. This was briefly touched on by James. And then why we care about that. Then I'll go through some structural control versus electrical control methods for uniformity. Then we'll look at adding some particularly interesting gases, fluorine-containing gases. I should mention this first part will all be in argon, very similar. Start simple, move up in complexity, and then I'll conclude. That's the wrong way again. There we go. So this has actually been touched on several times today. This is a slightly different graph. This is just the compound semicon, so actually it's quite useful as a follow-on from James there. Those numbers are in billions. And as you can see, the different, I didn't choose a color scale. Why you would choose 3 different shades of blue, I don't know, but they went with that. You can see here that the compound semicon market is growing quite fast. And in fact, by 2030, it's predicted to be well over 100 billion. So this is an area that's very rarely talked about. Silicon is pretty much all your bread and butter, but this is a hugely important aspect of semiconductor manufacture. And if we look at a wafer inside a chamber, you'll see that the wafer has a particular size to it. For the interest materials here, just list a couple, there are obviously many. Gallium arsenide, gallium nitride there are increasing in size, gallium oxide, silicon carbide, indium phosphide. You'll notice that they're increasing in size by quite a large margin in many cases. In particular, indium phosphide is making a very, very large jump, doubling in size potentially, as James alluded to earlier. Exactly how many useful chips you'll get out of the 150 mil wafer is unknown, but they are making that jump. Now, what you'll see here is a picture that's quite old now. This is a wafer inside a gaseous electronic cell in argon. The color contrast on the screen might not show it as well as I hoped, but hopefully you can see that there is a discharge on top of this very small wafer that is extremely inhomogeneous, right? You've got a glow in the middle and it tapers off towards the edge. So you've not got particularly homogeneous plasma touching that wafer. So any ions hitting the surface of that wafer are going to have different fluxes, different energies, because of the different densities and different sheet thicknesses in front of the wafer at different points across its radius. This is not good. This means that you're going to end up with inhomogeneous etch on the surface, which means you're going to end up with wasting elements of your wafer. The ideal case is to control this to make it as flat as possible. And that's what the rest of this talk is going to be going on about. Increasing this size naturally makes this problem worse. So here's a random picture of a wafer. It actually isn't silicon carbide, but it's a nice picture that I grabbed. And again, James alluded to this earlier. The cost of these wafers is rapidly increasing. I wish it wasn't good. So the standard approach for developing a recipe would be simply to adjust your power, your pressure, your gas admixture, your processing time, process your wafer, study the results, suggest changes, repeat, and just keep doing this iteratively until you get a recipe that works. This is fine if you're working with silicon wafers that are tens of dollars to hundreds of dollars. But if you're talking about wafer sizes now that are increasing for expensive materials like silicon carbide and indium phosphate, gallium nitride, which are layered as well onto silicon, which makes them even more expensive, you're talking thousands, if not tens of thousands of dollars a wafer. So if you've got to go through an iterative process of thousands before you get something that works, then you've bankrupted your company before you have a recipe to sell. This underpins why we might want to simulate these, because you can run simulations of these wafers for pennies, and possibly dollars for very expensive ones, not tens of thousands. Wrong way. I just want to underline here as well the rapidly increasing parameter space that is being felt in this area. So not only do you have the different processing gases that have been alluded to today, you've got your fluorinated gases, your chlorinated gases, ammonia, methane, all these things that we talked about today, but also the space of potential interest materials is huge. So for each of these individual materials, you've got hundreds of different steps involving tens of different gases, and all of these have on top of them multiple different ways to operate in pressure, flow rate, etc. It's just an n-dimensional Cthulian nightmare. And so basically, we're scaling our dimension here faster than our understanding. There's no clear consensus and a general solution forward. Although Mark Kushner, as alluded there, thinks that improving this process by using a physical interpretation, ab initio interpretation for a small number of data points is potentially a way forward, and then filling in the gaps. So let's have a look at some results of trying to control a uniformity on top of a particular wafer. Everything I'm going to show is using the hybrid plasma equipment model. This has been introduced already. I won't go into this in any detail. If you want to ask, you've got one of the world's experts and creator in the room, so you can go and speak to Mark about it, or you can speak to myself about it. But basically, the simulation is going to show you are going to use both the fluid and a bulk fluid approximation for the electron energy. Some of the later ones are also going to use a Monte Carlo electron energy as well, and everything else is as shown there in color. The first results I'm going to show you using argon, and then we're going to move to a better gas later on. Yeah, I'm not going to show you the whole reaction because it's a bit boring, but basically it includes ground states, some metastable states, single and dimer positive ions, and then it includes these classes of reactions. It's quite a comprehensive argon set, and it was developed actually in a paper there by Mark Kushner and Ken Tiang. It's actually the one that Mark himself cited with the UV. And so we're going to be doing it in this geometry. This is a very industrially relevant and not actually industrial geometry. So it's a CCP geometry with a powered electrode on top, grounded electrode on the bottom, a dielectric focus ring, and grounded walls. So a nice simple geometry just to be testing with. I'm going to run this at 300 watts to positive power with a single 13.56 megahertz driving frequency. This argon is going to be at relatively high pressure with 1 torr. The other stuff will be at a lower pressure. I apologize for the pressure changes. This is sticking some work together. So if you do this, you get a discharge, fantastic. You can see here argon ion density, peaks at the edge. This is similar to what you've shown previously. You get this kind of red blood cell shape where you get peak in argon density out to the high radii. This is simply due to a displacement current field going backward and forward between the powered electrode and the adjacent grounded area. If you look at the bulk ionization, then bulk ionization reflects this displacement field back and forth, back and forth, back and forth. You get a bulk ionization here, and then you get a bit of sheath ionization directly in front of the powered electrode. This is due to mostly capacitive heating in front of the electrode, as the sheath expands and contracts during the RF cycle. Great. This is quite an inhomogeneous setup. You've got a radial variation in your ionization. Now, secondary electrons are being emitted in direct proportion to the argon ions hitting the surface. You can see here the ionization by the secondaries. Ignore the bit in the middle, that's just a numerical flip. But across the surface, you'll agree that's quite a uniform distribution. So you've got a non-uniform bulk ionization, and you've got quite a uniform secondary ionization. Great. Next, if you look here, I've made this quite fiery. I've deliberately gotten rid of the flux going up the way. This is just the argon ion flux onto the table, make it a bit clearer to look at. Hopefully you can see that the arrows indicate that the flux is pretty much going normal to the surface, and you'll see there's a very large flux here just below where the argon ion density is. Obviously, you've got more ions, you've got a higher flux. Duh. Doesn't take a PhD to figure that one out. However, this is a problem. Because obviously, as I mentioned earlier, if you're wanting to increase the size of the wafer, if you increase this reactor, you end up with a larger radial inhomogeneity. So what we're going to do to make this simpler, I'm going to try and not show too many 2D figures. I'm going to try and abstract them away. I'm going to take a 1D slice in front of the wafer, and I'm going to show you the flux. So it looks like this. Now, this is the flux. Negative means pointing down, so more negative means more flux. So this is just analogous to literally what you've seen before. In fact, it's the simulation from before. And I'm going to define also a uniformity. Uniformity is the max flux minus the min divided by 2 times the average. It's a fairly standard unit to tell you how flat a line is. 0 means a flat line. Above 0 means a non-flat line. So 0 good, not 0 bad. And it's actually subjective where you measure the uniformity from. So a lot of people tend to quote uniformities that are probably better than they actually are just by choosing a different cutoff point. Just want to point that out. I also want to point out the value, the 0.4 here is reasonably good for sort of CVD and PVD. But if you're looking at ALE and ALD, so atomic layer etching, atomic layer deposition, which seems to be talked about most today, you kind of need a much better uniformity. You need something in the range of 2 to 1% uniformity for those processes. So this would not be suitable for an ALE, but might be suitable for a CVD, for example. Okay, one last thing I want to mention, the hollow cathode effect. If you have an electrode that is split in 2, or you drill a hole through it, and you've got the electrode powered on both sides, secondary electrons will come off as it's bombarded, as we saw earlier. However, they'll come off and they'll race across in a couple of nanoseconds, and they'll see the other sheath, which is still powered, because a 13.56 megahertz is a 74 nanosecond cycle. So the secondaries will race across, they'll see the other side still negative, they'll go, oh no, and they'll fly backwards. And then a couple nanosecons later, they'll do the same thing. So one electron can do a lot of work. It can be accelerated multiple times, and it can do a lot of chemistry, a lot of ionization. This leads to an enhancement of the plasma density inside these hollow cathode structures, as alluded to in James's talk. Quite well known, a lot of work done on this. And in fact, I didn't set this up, but there's the same figure that James talked about earlier. So this is now actually being used and applied to industry. I promise we didn't set this up. This just happens to be how close things are. So there are many open questions regarding the cavity distribution, shape, and size, however, and again, this was highlighted. The parameter space here, just with the distribution, shape, and size of these holes is massive. Keep in mind, this is only for one gas in one process, for one material, and this is already a huge parameter space for just that one thing. Massive. So let's take this forward and add a hole into our previous simulations. So one simple hole, I've got three variables that I care about. I've got the width, the depth, and the radius, center radius of the hole. I can move the center radius, and I can also change the width and depth. So I'm going to be playing with these, and I'm going to see what these do to the uniformity. Nice and simple, all in Argon. So this is what we had previously. Remember, flux at high radii, flat in the middle. Let's add some holes. So if we add a cavity, and I've roughly shown where the cavity is, this is all to scale. So the cavity is a high radii, and it's a 9mm arbitrarily chosen width. If I change the depth, you will see the red line is flat. So that means it's good. It means that we can process things. It means we can make more money. It means we can do more interesting stuff. But what you'll notice is that one of these is better. The other four are worse. So this is an extremely sensitive control mechanism, right? You have to be extremely careful how you design these electrodes to get a good result. You will more often than not get a bad result. And here's just a picture of what that will look like. You can see here that the electron density is in fact ever so slightly enhanced, but more or less the same max value, but it's been localized. And actually, it's difficult to see here, it's been pulled upwards. What this does is it pulls slightly more of the flux up towards the cavity, and then it takes away a little bit of the flux that would have gone down towards the surface. So this might seem counterintuitive. I put a cavity that would create more plasma on top of the place where I had the higher flux, and the flux goes down. It's because with the right sized cavity, you draw a little bit extra flux into the cavity. The problem is, with the wrong sized cavity, you create way more flux and completely screw your, your system. Weirdly, one of these worked. This is my attempt at making it go wrong, and one of them accidentally worked. Anyway, you can see how easy it is to have this go wrong. What I thought I would do next is then I would map this. So what I did for one cavity centered on R86mm, so the same one I showed you before, I varied the depth and I varied the width, and then I made a 2D plot. This is showing that uniformity value. So again, green is good, 0 is a flat line, and the blue is a curvy line. So there's an ocean, don't fall in the ocean, you'll drown. Land is good, ocean bad, okay? And here we've got a minimum uniformity in this little island of stability of 1%. Good enough for ALE, good enough for ALD. Fantastic, we've solved it. We now know how to make it. We know what size to make them, we know where to put them. No, we don't. Because if you move the cavity to a different location, just one cavity, one simple gas, and one wafer, you end up with what used to be your island of stability is now a lake of sadness, and you will drown. So what instead happens here, if you move the cavity towards the center, you have to navigate this little archipelago of stability, and you still get pretty good minimum uniformities, around uniformity of 2%. So still good enough, but a totally different design. Keep in mind, this is just for Argon. This is the simplest possible case. And one hole, I'm not even looking at two holes. It's insane. So this is just one hole, moving the radius of the hole, you get totally different landscapes. This underpins what Mark was saying earlier, that we really need to be able to kind of think of these problems in a much more kind of machine learning perspective. We need to use some sort of physical ab initio model to put a few points on this map and then fill these maps in with the machine learning rather than doing all of this brute force, because this is a lot of simulations. This is several hundred simulations to me. Okay, now we're going to move on to electrical control. Great, you can dig holes in your electrodes, it works, fantastic. What if you don't want to dig holes in your electrodes, or what if you want to use the electrodes for multiple things? You can apply Taylor voltage waveforms. Many of you will see these before, some won't. What you do is you just add a bunch of sine waves together, different voltages, with a phase offset or an amplitude offset, you get a shape. If you do this, then this is the sheet potential versus the applied voltage phase. For these, colors match. You can see that the average phase, the average potential of your sheet will vary, but also the points in the phase where the sheet is collapsed and expanded will also vary. So you have two different control mechanisms there. You have a sort of phase average control mechanism and an inside phase resolve control mechanism. and they affect the volumetric and the secondary processes differently. Here is the DC self-bias measured on the surface of a capacitive discharge electrode, for applying these waveforms with different phase offsets. And you can see you get quite a large control here over the DC self-bias. And as I mentioned, inside the RF cycle, you also get control over what's happening at different points in phase. This can be used, again, self-plug. You can use this to control the mean and the mean energy particles hitting the surface, and also the flux. So in the past, if you wanted to get a high flux at, say, 108 megahertz, you would increase the voltage going along this line. Unfortunately, a high flux would come with a high energy. You had no choice but to accept it. If you use dual frequency waveforms, then sometimes you get control, sometimes you don't. We demonstrate here that where you can lose that control. If you keep adding harmonics to true tailored waveforms, eventually this opens up into a circle. And so here you can have a range of different fluxes at roughly the same energy, which is extremely useful. Now, we know we can do this energy flux control. Can we also do uniformity control? So what we're going to do, we're going to take our previous case, the 2D case that I showed you before. No holes in the electrode this time, just a flat electrode, same as the first case that I showed you. We're going to apply tailored waveforms. If we do that, and this thing works, there we go. If we do that, we get the following. Now, notice that this is a log scale, because applying different waveforms applies a different DC self-bias, so it changes the flux of the surface quite significantly. So you do change the flux quite significantly, but the uniformity here is shown because the log plot smooths out the lines, so they all look flat. This uniformity here, you can see, as compared to the base case, varies by quite a large amount. So you get a very large control of the uniformity. And in fact, again, your best case at 90 degrees there is good enough for ALE, ALD in this particular configuration. And what you will see here, I've tried to put a couple of different factors at play. You get two ideal cases. This case here at 90 is using the waveform morphology to control the uniformity, but it's got a large DC self-bias, like a very negative one, so you get a very large flux. Whereas the green one, the morphology of the waveform is roughly the same, so you get the same control and uniformity, but it's introducing a more positive DC self-bias, or a small DC self-bias, and so you end up getting the similar uniformity but a total change in flux. So here, not only can you control the uniformity, but you can also choose, in this particular case, if you want a high flux uniform plasma or a low flux uniform plasma. So it gives you an extra control knob on top of the uniformity. Very nice. And you can see, again, quite sensitive to changes, but these changes are real-time control. This is a knob. This phase offset is literally somebody in a room going on a waveform controller. So this is a real-time thing. You don't need to dig a hole in an electrode to do this. You can take a machine that exists and you can turn it into this by applying a different power supply. Cool. That's all in argon, though. Will it work when we do it in a real gas? I don't know. Well, actually, I do. You don't know. You'll better find out. So we applied two different gases. This is the work of one of our students, actually, a fantastic student, Charlotte Lindsay. She did a summer project with Oxford Instruments Plasma Technology, which this evolved into this work that you're seeing here. So everything here is her simulations, and I'm just taking the credit. So we applied SFX and NFX, SF6 and NF3. I'm not going to go through all the reactions of these mechanisms, because half of Mark's talk was just talking about reactions, so this would be very long if I did that. Safe to say, these are slightly less detailed than the ones Mark were talking about, but they're still good enough. And we couldn't use the full reactions because, again, of the time constraints of doing all of these different simulations, we had to use a slightly trimmed down set. So we contain all of the SFX and neutral fragments and their respective positive ions, but we only have the SF6 and SF5 negative ions, F minus, F2 minus, so F2 single minus. And we also have the NNS neutron positive ions considered within the set. And we have these types of reactions. Of particular importance are the dissociative attachment and collisional attachment, as I highlighted earlier as well by Ryan. The collisional attachment ones are not particularly well known, but they are included. So if we now take the same case with the same conditions, now a lower pressure, 10 millitorr, I apologize for the pressure, but with lower pressure, this is an SF6 discharge, same conditions, 300 volts, 300 watts, 30.56 megahertz, with SF6. You can see that the fluorine plus now, not the argon plus, massive difference, right? So the argon density here, I mean, you've still got the kind of red blood cell shape, but the radial distribution of the F plus is massively different than before. And this doesn't look very uniform. And in fact, yes, if you look at the flux here, it does not look uniform at all. You've got a lot of flux out of this outer edge hitting the surface. You've not really got much here at the center of the wafer. So a very inhomogeneous discharge. This is probably because 300 watts is too low for power to use SF6. We're not quite dissociating it. So you've got a lot of fragments kicking around. So the F plus is not necessarily penetrating fully in yet. However, what we're going to do is we're going to reapply the tailored voltage control and see if we can fix that. So really inhomogeneous discharge. I'm not going to use a peak and valley. I'm going to use this modified sawtooth. So this modified sawtooth has this term here. I won't explain why it works. It's something I came up with ages ago. Basically, what that term does is it makes these wiggles less wiggly for the same number of harmonics. So for the smallest number of harmonics, it makes this a closer to a true straight dB/dt, which is what you want. Now what I do, I'll show you this again. This is the fluorine, not argon, I apologize, that's fluorine. The fluorine plus ion hitting the surface. This is the actual flux hitting the surface. And then again, the uniformity plotted there. Remember, lower, better, zero means flat line. You can see that the dotted line there is a single case I showed you before, extremely inhomogeneous. The uniformity there is 0.6, which is impressive how bad it is. But when you apply sawtooths, for all sawtooths tested, the uniformity was better. And for a very small range of phase offsets, the uniformity was very good, in fact, down to 2%. So again, we're getting into the ALE, ALD. So we're completely controlling the discharge at the edge of the electrode. If you recall back to when I mentioned that there were two different ionization processes, there's a bulk one due to the displacement field, and there's a secondary electron one. We are modulating between how much is going into secondary ionization, how much is going into bulk. And also here, we're modulating how much dissociation is happening as well. It's very complicated, but basically, by modulating the phase offset, you're modulating how much energy is going into bulk versus secondary processes, and you get an ideal case here where you begin to reduce the asymmetric processes and enhance the symmetric processes, which leads to this very narrow range of phase offsets for which you get truly quite a flat profile. Great, and then here's the two cases. This is the worst case, 60-degree phase offset, 240 offset. Just wanted to really highlight that it really does change the uniformity quite significantly. This is the flux hitting the surface here is pretty much normal. The flux hitting the surface here is not. It changes everything about the discharge. I haven't got time to go into it, but the potential changes, the charge to the surface changes, the distribution changes, everything changes. The whole talk just on this alone. Great, so we've solved it for fluorine then. Why don't we just try NF3? We had it lying around. Let's go ahead and see what happens when we do that. So NF3 then, NF3 was applied in the same conditions, so 10 millitorr, 100% NF3, 300 watts, 13.56 megahertz, same reactor. You'll notice here the distribution of F plus is now quite considerably different again. So changing the gas from SF6 to NF3, what we found is the NF3 actually dissociated slightly better, and so the F plus was able to penetrate further into the center of the discharge, and you've got a different distribution of your density and your F plus ions. This was unexpected. However, it does seem to follow from what we've seen previously with other NF3 SF6 discharges at higher powers. Normally, SF6 tends to dissociate further. At lower powers, this seems to follow. If you look here at the flux again, this is what we saw previously. The SF6 flux is highly asymmetric. The NF3 flux has two regions. So you've got one region here below the peak density, which is, of course, high density, high flux. Interestingly, though, the flux of the NF3, despite having a low density at high radius, is actually still pretty high. And this is just due to a charging of the wafer. The ions are drawn out from the bulk. You can see here the flow lines are being drawn out from the bulk and then hit. Now, we have done ion energy distribution functions and velocity distribution functions on that surface. I wasn't able to show them today, but yes, you end up with ions hitting at an angle. So while the flux out here is high, if you were to look at the holistic picture, this is all flux, remember, I haven't even talked about energies. If you look at the holistic picture of the angles and the energies that the ions hit here, they'd be hitting at some angle, they're being drawn across due to the surface charge on the wafer. So that's why that's happening there. Okay, so tailored voltage control again. What we've done is we've applied the same sawtooth waveforms as before, and we've applied them with the same conditions as before, and we've now got our, again, not argon plus, I apologize, F plus for NF3. What you will notice is that the baseline, the uniformity, much better, as you would expect from the distributions that we saw previously, and you'll see that most of the sawtooths we applied are in fact worse, higher numbers, that's bad. There's only one case which is actually better for the sawtooths. This is good because the one case is all you need, but it's bad because it's mostly not helping the situation. It's mostly making the situation worse. And if you look at here, you can see that the distributions are kind of as before. The other interesting thing about the sawtooth is that the DC self-bias is not modulated as much with the sawtooth as it is with the peak and valley. And so the fluxes for the sawtooth cases are actually closer together. I should have mentioned that when the first sawtooth results came up previously. So I don't want to go into much more talking about this because you've seen it before, but as you change the phase offset, you change the bulk versus secondary and so on and so forth as you change the uniformity. What I do want to focus on though is this. These are in the same reactor, with the same wafer, with the same pressure, with the same power, with the same shaped waveforms, each of these dots being the same shaped waveform going down. So this blue one is the same as that one as well. And they are exhibiting opposite trends, completely opposite trends, right? And keep in mind, this is just SF6 and just NF3. Normally, you'd run these with an oxygen admixture and a variable oxygen admixture. And you could run these with different pressures. You could run these with other different surfaces. This isn't even taking into account what comes off the wafer. The wafer here is a sort of static object. In real life, the wafer would be giving off silicon, would be giving off carbon, would be giving off nitrogen, would be giving off something else. That changes with the energies, so that changes with the biasing, that changes with the temperature of the wafer, if you've got a cryogenic wafer or a heated table or anything. 1,000,000 to 12 different parameters can change. And I've kept as much as I possibly can the same, and I've trimmed these two reaction mechanisms down to be only about 150 reactions each to make them nice and simple to compare. And yet, even under these idealized perfect conditions, where we're comparing as like for like as we possibly can with two fluorinating gases, we end up with 180-degree out-of-phase control results. The best case for SF6 is the worst case for NF3 and vice versa almost, right? This is insane. And so basically, there is no general solution that we have found for a control mechanism when you just change a very small aspect of your discharge. And I know changing the chemistry gas is not maybe very small, but you're only changing one thing in theory, right? These should be a lot similar than they are. So I'm going to come to the end and the conclusions. What we've done is, and I think this is actually faster than I was expecting, which is good. So the conclusion is that we've looked at discharge uniformity in a CCP reactor with argon, and we've done work here with a hollow cathode, where the hollow cathode shape was varied, and what we found is that we were able to control the uniformity by changing the shape of the hollow cathode and changing the location of the hollow cathode. However, the location and shape massively changed the uniformity maxima and minima. We've also found that with electrical control, we have a large degree of control over the uniformity for different fluorinated gases and for argon, but that the degree of control varies massively depending on the gas that you put in, all else being equal. Therefore, if you're going to have any control mechanism, it's going to be completely specific to the process that you are currently doing. If you're using a gallium nitride, if you're using silicon dioxide, or if you're using silicon carbide, or whatever you're using, with a particular gas at a particular pressure for a particular recipe, if you change that recipe in any way, the work that we've done here shows that your control mechanism may completely change as well. This underlines the need for a continued development for fast, rapid, and hopefully machine learning adapted systems that we are able to then do a small number of samples over these systems for a given recipe, a given material, and then fill in those gaps efficiently and quickly on an industrially relevant timescale to be able to dictate the control mechanisms, which are going to be sold along with the recipes for that specific process, right? You basically have to have a recipe for your process and a recipe for your control mechanism, and they have to come together. There might be generality in here somewhere, but even finding that generality is probably an ML problem because you're going to have to feed it loads of control mechanisms, loads of variations, and try to find something. So with that said, hopefully you enjoyed my talk. Any questions?